Okay, slight technical problem.
Okay, so let us not introduce Helena, please.
Thank you for the non-introduction. Okay, welcome to the third and last installment of these lectures. So today I'm going to talk about vorticity. No more velocity, no more energy, or not much. Okay, so, all right, so if we consider some conserved quantities for vorticity, vorticity is transported, of course, by our diffree favorite vector field U, okay, and then smooth solutions, as we've already noticed, do conserve LP norms. Conserves entropy and all other LP norms. It conserves more generally any function of omega and any rearrangement of variables. Okay, so the natural question is let's try to find regularity conditions so that these are conserved at the level of weak solutions. Okay. Or generally, what we want to know are conditions for the weak solution to be a renormalized solution. So I'm going to define that in a minute. Okay. All right. So what are renormalized solutions? So if we look at this transport equation, so this is a linear transport equation. The vector field V is given and it's divergence free. I'm assuming it's divergence free. So a measurable function W is a renormalized solution of my transport equation if when I compose it with any C1 bounded function beta, then beta, the composition satisfies the same transport equation. So these are sort of like chain rule kind of solutions. Okay, so you multiply the equation by beta prime of W, and you get that that beta of W is a solution. Okay?
Can you be more specific about the equation holds in what sense?
Okay,
I
so
mean,
the
because,
equation holds
first,
in a weak sense,
which is in this
distributional
case.
sense,
So,
sets of distributions.
I mean,
So-
B, what is B? B is smooth or not smooth?
I'm
that
not
makes sense?
I'm not specifying this at the moment. Okay? I'm not specifying
So B plus
conditions.
grad W should be distribution.
Basically, yeah. Well, B should be a distribution, right? Because beta is going to be smooth and bounded. So basically, for a very large class of B's, this is going to be okay. If you want, so that B times beta of W, B times beta, B is divergence free, B times beta is
That's
L1.
what, because you didn't, so that's what I was asking.
But I don't want to get into that right now because I'm going to be a lot more precise in a So consequences of being a renormalized solution are that if B is divergence free, then any rearrangement invariant norm of W is conserved. That's pretty clear because basically, well, for instance, if you're in a bounded domain, you can take S function 1, you can integrate this, and you just get any T of the integral of beta of W is 0 for any beta C1 bound. For the LP norms. Additionally, you have uniqueness for the linear transport equation. So there exists a unique renormalized solution. This is a result by, this whole theory is due to Dupin and Lyons, a paper that they published in 1989. You have a Lagrangian formulation of transport. So there is something called the Lagrangian trajectories. Notion of Lagrangian solution. Okay, and now I'm going to be more precise. Okay, if W0, if initially your transported scalar quantity is LP, and V is L1 in time, W11 log, divergence 3, then there exists a unique renormalized solution who lives in continuous in time into LP. All right. Furthermore, renormalized solutions are consistent with weak solutions in the following sense. So if W is L infinity into LP, and B is L1, W11 log intersect LP, then being a renormalized solution implies you're a weak solution. More interestingly, If your B happens to be L1, not only L1 in time into W1 loop, but L1 in time into W1 P over P minus 1, and this exponent here, P over P minus 1, is a Lebesgue dual to LP. Okay. Then W being a weak solution implies it's renormalized. So in particular, if you have B in this nice class, W1 P over P minus 1, then there exists a unique weak solution, also of your linear transport equation. Okay. So let's take omega naught and LP, P greater or equal to 1. We know that we have a weak solution of 2D Euler. It's constructed by Almeida, Delors, Udovich, Becky Wu, etc. Okay, and associated to this vorticity by the Gauss-Savart law, there is a velocity, okay, which is divergence free. So if I view this as a linear transport equation for omega, the vorticity equation, with a transporting velocity u, okay, then back in 05, Anna Matsukato, Milton, and myself we proved, well, you noted actually, it's not even a real result, it's just basically observation, that if P is greater than or equal to 2, then every weak solution is going to be renormalized. And this is basically just reading the consistency result of Dupert-Lyon, sorry, because if the vorticity is an L infinity LP, then you can upgrade the velocity to L infinity W1P. And if P is greater than 2, then you're in all the LPs below. You're going to be in W1P for all the P's below that P, all the Q's below that P. And in particular, if P is greater than 2, you're going to be in W1, P over P minus 1. That's going to be less than 2. So that's the proof. Okay. All right. So corollary, if P is greater than 2, we already know that the LP norms are all conserved. Furthermore, if P is less than 2, then if you're a special kind of weak solution, namely obtained as a weak limit of smooth, exact solutions of 2D Euler, then you're also renormalized. Okay. All right. So the proof is stability. So Dupert-Lyon also established stability of renormalized solutions. If you have a bunch of renormalized solutions converging to something, then the something, the limit is going to be a renormalized solution. If you're smooth, you're renormalized. Okay. All right. So at this point, we pose the question: can you prove for P less than 2? Can you prove that other kinds of special weak solutions, namely the ones that we're most interested in, which were physically realizable weak solutions, they're also renormalized? And this was answered affirmatively by Gianluca Crippa and Stefano Spirito in a paper from 2015, where they showed that every physically realizable weak solution with a vorticity, which is L infinity LP, P greater than 1, is renormalized. So all of the LP norms are all conserved. Okay. So I'm going to say a lot more about this, but in brief, their proof uses the Dupert-Lyon's duality formula, which I will comment on. And actually, this is a pretty powerful tool, if you think about it, in which I think we're only beginning to learn how to use. Okay, you have to consider the viscous and the inviscid adjoint problems, and passive adjoint viscosity limit in the linear adjoint problem using uniqueness of renormalized solutions. I'm going to say a lot more about this in the coming slides. And no need to pass the limit in a linear term because you only look at the linear adjoint problems. Okay, and then in 2018, Crippa and Spirito, together with Camillo Nobili and Christian Seiss, upgraded this to include L1, equal 1. So if the vorticity is L infinity L1 and it's physically realizable, namely it is a weak limit of vanishing viscosity solutions, then it's going to be renormalized. Okay. The proof is complicated. It involves an extension of the Dupert-Lyon's theory to flows which are not now L1 into W1 loop, because if the vorticity is only L1, then the Calderon's inequality does not allow you to conclude that the velocity is going to be have a derivative that's fully L1. Okay? So basically what they did was they extended the Duperle-Liouville's theory to allow for flows whose gradient is a singular integral operator acting on an L1 function. It's a pretty powerful result also. Okay, so they used it to deal with L1 vorticity, and then from there they managed to get all the estimates that they need. In addition, you're going to have a sequence of vorticities omega nu, which is going to be bounded in L1, and that doesn't allow you to conclude that you have weak convergence in L1. So they need uniform integrability, which they also show. All right, so I want to delve deeper into the Kripa-Spirito result. Okay? And for that, we need this other result called duality. So suppose you take a B, which is a nice transporting field. It's L1, W1 the log. They did it more generally for divergence of Bs that were L1 into L infinity. Okay. Our interest is going to be divergence of B equals 0. Suppose P is greater than or equal to 1 and choose a test function F, which is smooth and compactly supported. And I'm not making any statements here about my underlying physical space. Okay? I'm thinking mostly of the torus because that's just the easiest thing to think about. If your physical space is the full plane R2, you have to deal with issues at infinity, and I don't want to get into that. But there are corresponding results in R2. So suppose you have a normalized solution of the equation dtw plus b grad w equals 0, okay, with w L infinity LP. And suppose you also have a solution of the adjoint problem, which would be dt phi plus divergence of b phi plus f, we're given f. And phi is in the dual space LP, so it's going to be L infinity in time, LP of p minus 1. Actually, it's enough to have an L in 1 in time, LP of p minus 1. Okay. Then for every t, the duality formula holds true. Okay. So this is, again, another sort of obvious theorem that all engineers know. But if you want to justify it at this level of irregularity, you need to go through the renormalized framework. All right, what this amounts to, why I'm saying this is obvious, this just amounts to multiplying this equation by phi and this equation here by w, and then just noting that you have, you can integrate and integrate, and then you have exact derivatives. Okay. The problem is justifying all of these multiplications. Okay. Now, let's look at Kripa-Spirito's results. So stated properly, I take an initial velocity, which is L2, whose initial vorticity is LP, P greater than 1. Let U be a physically realizable solution of the Euler equations with initial velocity not, and U to be a physical realization. And assume that omega not nu, the vorticities and viscous initial vorticities are bounded in an LP. Then, okay, so we're normalized solution, and in particular, the LP are conserved. Let me give you the proof. First of all, without loss of generality, I'm looking at p's less than 2 because otherwise it's reduced. This was already treated in our observation built in the knot. So let's consider a physical realization. Look at the curl, vorticity, and it satisfies the vorticity equation. Okay. So omega nu is going to be bounded in time to LP. That's just the maximum principle for the LP normal vorticity. And this implies that the corresponding velocities, the viscous velocities, are bounded in infinity W1 upgrade one derivative. Velocities one derivative is better, vorticity. Plus, the PDE gives you information on dt nu and actually on dt omega nu. That should be dt omega nu. If uniform control with respect to nu in some negative Sobolev space, it doesn't matter which. So you get that U nu is compact in C0 L2. Actually, this is So I have U nu is bounded in L infinity W1P, dt nu is under control, and W1P, P less than 2 is compact in L2, P greater than 1 less than 2 is compact in L2. Use this several times now. So this is something called the abelian limit. You also get C0 into LP because P is less than 2. L2 is locally contained in L. Okay, so let's assume that we have compactness. Let's assume that I've already passed through a converging subsequence, U nu converging strongly, uniformly in time, strongly in L2, and also strongly in LP. And additionally, I know that the limit is going to be, because everything is bounded in L infinity W1P, the limit is also bounded. There's also an L infinity W1P. Okay. And additionally, the vorticities will converge weakly in L infinity L. So I have weak convergence of vorticity, strong convergence of velocities. Okay. And the limit is going to be exactly control of U. That's just linear. All right. So omega is a weak solution. That's where I started off with. A weak physically realizable solution. And I want to show that it is a renormalized solution. When I take a test function f, C infinity compact support, and I'm going to fix some capital T. And I look at the dual problem or the adjoint problem, backwards linear Navier-Stokes type equation, where I'm going to use the transporting field as my union, a solution of Navier-Stokes. I look at dt something plus u dot grad something plus new Laplacian, so Laplacian with the wrong sign equals f, and of course I have to give it terminal data instead of initial data. Okay, I'm going to take the terminal data to be 0. Okay, so first of all, since f is smooth, okay, I always have a solution to this, and I can do energy estimates for it. If I multiply, I take any q greater than or equal to 2, and I multiply by this factor here, then I get the following estimate: minus ddt of LQ norm to the qth power of phi, my solution, plus some constant times nu. This is what happens with the dissipation term. It's not really dissipating here. Okay, equals to minus q f times this factor. Okay. And I can throw away this term. This is non-negative, clearly, so I can throw away this term, and I find out that minus dt of the LQ norm to the qth power of phi nu, the norm, is less than or equal to q, FLQ, and phi LQ to the power of q minus 1. That's what happens when you do Holder inequality here. But on my left-hand side, I have ddt of LQ norm to the qth power. So this is the same thing as q times the LQ norm to the q minus 1 times the dt of the LQ, and I can cancel these guys on each side. They're not going to be 0 because otherwise everything would be trivial. Therefore, I find for any lowercase t less than or equal to capital T, I can integrate this in time, and I get the LQ norm at time capital T with a minus sign because of this minus, plus the LQ norm at time lowercase t is bounded by the LQ norm. There's a constant missing. Actually, no, there isn't. So the L1 LQ norm effect. Okay. And this guy here is 0. Because I assumed that my terminal data was 0 for my PD. So this is just bound on the LQ norm of my solution at any time less than or equal to capital T. So it's bound. Of course, it's not negative. Okay, therefore I have phi nu bounded in L infinity into LQ for any q greater or equal to 2. The fact that my right-hand side, my forcing term, this adjoint problem, is a smooth, compactly supported function means that I can use any q I want. So from the PD, I get also uniform control for dt phi nu. Again, it's a Sobolev space, and therefore I can upgrade this into compactness C0 into LQ with a weak topology. Okay. So again, without loss of generality, let's assume that phi nu converges to phi and C0 LQ topology. Compactness, and we need to pass to a subsequence, but I'm assuming I already did. Okay, let's go back to my energy identity. This energy is decomposed. And integrate this in time. I'm integrating in time this estimate here, this identity. So when I integrate in time from 0 now to capital T, I'm going to get on this side, I'm going to get exactly phi nu 0 LQ to the qth power. I'm going to get an integral in time of this thing here and an integral in time of this. Okay, now let's use q equals 2. If I use q equal 2, this term is not there and this term is not there. Okay, and I get, and this term here, I just proved it's bounded by the FL1O. So in the end, I get nu times the integral in time with the integral in space. The gradient of phi nu squared is bounded by FL1O2 squared. So square root of nu grad phi nu is bounded in L2. Good. Phi nu is a solution of a parabolic problem, and therefore phi nu is smooth. So I can do things to it. For positive time, for any time actually less than capital T, my phi nu will be smooth. Even at capital T, it's smooth. It's 0. Let's take a test function, psi, and let's write down the formulation of my adjoint problem. Here it is. I just transferred all the derivatives that were landing on phi nu. I transferred them to psi. So I get this. Okay, and now since I took a test function which doesn't see time 0 or time t, there are no time terms at 0 or t. My nonlinear term is going to turn out to be a weak strong pair. Okay, all I have to do is, so remember that my u nu is bounded in L infinity W1 t. T is less than 2. So I have to choose a dual q, okay, which is going to be dual to this p. So this q is going to be bigger than 2. Okay, so I'm going to choose q to be p over p minus 2. Q is greater than 2, and I'm going to get a weak strong pair here. Okay. I have the u nu's converge strongly, C0 LP, and L infinity LP, of course. And phi nu converges to phi C0 LP over p minus 1. So uniformly in time, I have a weak strong, what we call a weak strong pair here. So this integral here, term here, is going to converge to the gradient of psi times u times phi. Okay. Of course, when under weak convergence, this term here is just a linear term that will converge. And the dissipation term will vanish. The viscosity goes to 0. Just, you can estimate this with a hard estimate. Nu times this term here is bounded by square root of nu times L2. Sorry, this should be nu, not square root of. No, I'm sorry, this is correct. Square root of nu times gradient of psi. Psi is given, so that vanishes. Okay. So finally, we obtain in the limit, when you set nu to 0, you obtain that the solution phi nu of the adjoint linear problem converges to this to a solution of this, satisfies this identity, and this translates to a transport equation for phi, namely this transport equation: dt phi plus u grad phi is f, and phi capital T is still 0. Now, my solution to my adjoint problem lives in LP over P minus 1. U lives in W1P. So therefore, they're in the right space to say that this is actually a renormalized solution. And since there is only one renormalized solution to this given transport equation, that's it. And so the whole sequence, the whole family, phi nu converges. I don't have to pass to any subsequences ultimately. Now, I multiply the equation for phi nu by omega nu and integrate. I get this. I can put the derivatives on to phi nu, and that's why this is an adjoint problem, because when I transfer all these derivatives here onto phi nu, okay, I'm going to get exactly this. Minus phi t ddt phi nu. This term here gives me a minus u nu grad phi nu, and this minus Laplacian, when I transfer the Laplacian onto phi nu, I still have a minus sign. Times omega nu is equal to, now I see times 0, phi nu times 0 times omega 0, omega naught. Everything here makes sense now because the phi and the omega are in dual spaces. This is F. For the adjoint problem that I was studying, says that this object here is exactly my F, which was arbitrary, fixed, but arbitrary. So I just found that the double integral of F times omega nu is minus phi nu times 0 times omega naught. Now I can take vanishing viscosity here, and I find that the double integral of F times omega is minus the phi of 0 omega naught, because the phi nu converges in C0 alpha. So it's continuous in time. Omega naught is alpha. Okay. And I assume that omega naught nu converges strongly to omega naught alpha. So by the de Prunelle-Lyon's existence and normalized existence and uniqueness for normalized solutions, there exists a W, which is a renormalized solution to this linear equation. So now this U and this W are not necessarily linked by the Biot-Savart law. The de Prunelle-Lyon's theory gives me that there exists a unique renormalized solution to this equation. Phi, I had shown in the previous slides, phi is a renormalized solution to the adjoint equation. Therefore, I can apply the duality formula. It's the same equation, or if you want, it's the adjoint of this one because divergence is 0. The duality formula is okay. The duality formula then gives me that the integral in time and in space of F times W is this difference. Phi times t is 0, and omega and W at time 0 is omega naught. So this term here goes away, and this becomes minus phi of 0 omega naught. So that's the same as you have up here. What I've just shown is, I'm sorry, up here. What I've just shown is that the double integral of F times omega is the same as the double integral of F times W. This integral here is of F was a generic arbitrary test function to W is equal, omega is equal to W, and therefore omega is renormalized. And particularly the LP norms are conserved. Yes, Adam?
We have to find, I thought F was defined in our previous slide, or you said F.
Sorry?
You said F from the beginning? Or
Yes.
is that the part where you're going to stop me up? Can you go back a couple?
F is a test function given in advance.
F is the right-hand side of the adjoint problem for phi.
It is given in advance as any test function. That's how she defined the.
Okay.
So I would love this to be the result, but it's not. Because you said she is.
Thank you.
Okay.
There's a lot of this is in 7.
Anyways, we learn a lot with this. Why do we need P greater than 1? For P equals 1, I already mentioned this before, omega L1 does not apply that W1 once. We're in the wrong space for derivatives. This required, and also, of course, if it's bound in L1, you don't have recompactness in L1. Instead, you work with uniform integrability and an extension to take up. And so that's, no, I'm sorry. Okay, so summary. What do we know up until now? If you use a physically realizable solution, vanishing viscosity limit, and the vorticity is a weak solution in L infinity LP, then we know the following. For P greater than 1, in the previous lectures, we know that energy is conserved or balanced if you have forcing. If P is greater than or equal to 1, the LP norm of the Euler solution is conserved. I did not show you the case P equals 1 because it's a lot more involved, but that one was obtained, I mentioned this, by John Tipa, Pavila Nobili, John Seiss, and Stefan Speed. Okay, if P is greater than 1, I have strong convergence, actually, of the viscous solutions to the Euler solution. And if P is greater than or equal to 1, I have weak convergence of omega nu to omega Euler, and omega Euler is renormalized. Question: can the weak convergence of the vorticities be improved? Or is it only weak? So this question was first addressed by Peter Constantin, Theodorivas, and Tarek in 2019 in the case P equals infinity. And they proved that if the initial vorticity is bounded on the torus, converges strongly at L2, and you have a forcing term, which is L infinity in time, L infinity in space, then the convergence is actually strong in L infinity LP for any P less than infinity and greater than 1.
This G nu is the curl of natural physics.
The forcing here is the curl of the forcing for the velocity formulation. Their proof is quite complicated. They use some borderline regularity results for the use of our law. They developed new uniform short time estimates for the vorticity gradients, and they use an intermediate linear problem. And in 2021, joint work with Christian Seiss and Wiedemann, we gave a much shorter proof, which extended their result. So for P greater than 1 and less than infinity, we show that if the initial vorticity is in LP, with the viscous initial vorticities converging strongly in LP, and with the forcing term, which is L1 in time, LP in space, this is the same. Again, G nu is the curl of the forcing term for the velocity formulation of Neverstone's. Okay, and this L1 LP is the same regularity that we needed in the work on energy balance with forcing that I presented yesterday. The joint work with Milton. Okay. All right, then you get strong convergence. And actually, since we know that the limit is unique, it's a normalized solution, we don't even need to pass the subsequences. So, nearly simultaneously to our work, Gennaro Ciampa, Gianluca Scripa, and Stefano Spirito wrote a paper again in 2021 with virtually the same result, except that they managed to include people one. However, they do not treat forcing. No forcing in their work. So I'm going to discuss these cases, what happens without forcing, what kinds of complications arrive when you have to add forcing, and then I'm going to discuss their results. So let me start with the easier case. G nu is 0, no forcing. And let me show you our proof because for P greater than 1, because it's very cute and very short and very sweet. Okay, so I've taken initial vorticity, which is an LP. Viscous initial vorticity is converging strongly in LP. And I take a physically realizable solution U with curl omega E, and initial vorticity omega naught. Then omega nu actually converges strongly to omega E. Uniformly in time, LP in space. Step one is kind of immediate. First of all, you get the weak star convergence in L infinity LP. I've already discussed this. That's just because you have a bound L infinity LP for the viscous solutions. Omega nu will be epicontinuous from time into distribution space prime, that comes just from the PD itself, from the estimate that you get on the time derivative of omega. It's actually even better than two distributions, but I was late. Okay. Then we show, then from this you get, via O'Malley-Ohl's type lemma, Packness, Arizona, Scully, whatever you want to call it, omega nu converges to omega e in continuous in time, uniformly in time, into this LP space with a weak topology. Okay. Step 3 is a tiny bit more interesting. For each fixed time, the LP norms converge. So you start with the fact that you have omega nu converging weakly to omega e continuously in time, so you can evaluate it at any time. You get the weak convergence in LP, and the LP norm is weakly lower semi-continuous. So the LP norm of the limit is less than or equal to the limit of the LP norms. And I guess the superscript E is fell out. Okay. Of course, the limit is bounded by the lim sup. And again, the LP norm is decreasing in time. So this is bounded by the biggest one of all, which would be the omega nu naught, which in turn is bounded by omega naught. We know that the LP norms are conserved. So keep the speed. Okay. And therefore, all of these inequalities turn into equalities, and you get that for each time, you have the convergence pointwise in time. Also, the sup norm goes to 0. The sup in time, because for the Euler solution, the LP norm is the same always. Okay. And for the Navier-Stokes solution, the LP norm at time lowercase t is greater or equal to the LP norm at time capital T if the ordering is t less than or equal to capital T. Since I know that this guy here vanishes, I know that this one also vanishes, and so I have the sup in time. So it goes to 0, C0. Uniform. Okay. Now, pointwise, this implies that pointwise in time, the convergence is actually strong in LP, because the convergence plus convergence of norms implies strong convergence. And by the way, this is only true for p greater than 1. So this is another place where you need p to be greater than 1. Finally, I don't only have the convergence pointwise in time, but I also have it uniform in time. And proof of this, I'm abbreviating because this is a sort of a repeat of the lower semi-continuity argument I gave before. Okay, using definite continuity. It's actually done by contribution. Assume that it doesn't converge uniformly in time, so you find some kind of sequence of times at which the supernorm of the difference is bigger than, let's say, 1 over n. Okay, and then you derive a contribution. All right, so QED. So how much more complicated do things get if you add forcing? So if you assume now that you have forcing, remember that G nu is the curl of this capital F nu. And these forces, the viscous forces, converge strongly L1 LP to G, then you also have the strong convergence. Here's an outline of the proof. Proof goes like this. You begin by smoothing initial data and the force. Involved with some modifier. Language of this talk last week, just take a little pass filter. So the advantage now is that these guys here are all smooth and bounded. Then you go to these intermediate linear problems, this one and this one. So you start from your smooth initial data and your smooth forcing, and you solve a Navier-Stokes-like equation, but with a velocity field u, which is u nu. You don't do anything to this nu. This is not the same thing as involved with the equation. Okay, and then you solve this intermediate problem where you have again smooth forcing and smooth initial data, and you transport it with the Euler flow. So these are linear problems because the transporting field is given. Okay. Then you just use the triangle inequality to say that the LP norm is the difference between the viscous vorticity omega nu and the planar vorticity omega can be estimated by the LP norm of the viscous minus this W nu epsilon, W nu epsilon minus, sorry, W omega nu epsilon minus omega epsilon plus omega epsilon minus omega. These guys here are perturbations of the original equation. Just perturbed the forcing of the data. Okay, for this sentence. And this is where the rest of the story lies. So you show that this term vanishes and mu goes to 0 for fixed epsilon. Okay. And this is a small adaptation of the argument without forcing. You're going to, the data is smooth and bounded. So it's again, you're going to use the same kinds of tools. The lower sum continuity of norms, the convergence of norms implies plus weak convergence implies strong convergence. Pointwise of time, and then you get the uniform convergence of time again by an argument using it. So the heart of the argument is the G. Okay. And then you show continuous dependence for the intermediate problems. So here you need your forcing and your initial data to be smooth and bounded. Okay. And then the intermediate problems you can show discontinuous dependence. Okay. So that takes care. That's our work, QED. I want to make some comments on Siampanti and Spirit because theirs was a pretty hefty paper. On the one hand, they do not treat forcing. They also give two proofs: a Lagrangian proof and an Eulerian proof. The Lagrangian proof that the physical space is the torus, so they're looking at all periodic solutions. And P is assumed to be greater than 1. Okay? The Eulerian proof is where they managed to include the case P equal 1. And it's in the full space. They claim that P equal 1 works on the torus as well, but the proof that they gave, which is Lagrangian, it's complicated to carry out in the case P equals 1. That's still up in the The Lagrangian proof uses a stochastic Lagrangian representation of the viscous vorticity. Okay. So, and then they do a quantitative comparison of the distance between the trajectories. Pretty neat. In the case P equal infinity, they actually get a quote rate, a quote convergence uniform time to LQ. Okay, but the rate depends on this L1 modulus of continuity of omega naught. So taking initial vorticity, which is an L infinity, you define a modulus of continuity in L1 for this vorticity, and the rate is not explicit. It's given in terms of this modulus of continuity. USB less than infinity. The Eulerian setting is where they include the case P equals 1, which we did in our work, and the fluid domain is the full plane. Their proof again is very reminiscent of our proof. It uses the intermediate linear problem plus the uniform integrability of omega nu and an extension of interpreter. Making their proof work with forcing for P equals 1 is somewhat delicate, and actually it's not fully written up, but we've managed to do it. And we is joint work that's actually still in the works and still being written up with Christian Seisen, student of his, Victor Navarro. And in the process of writing their full plane result, they actually needed to provide an extension of the energy conservation result by Milton and myself and Roman Shidkin and Alexei Sheshkinov. We did it for flows which were torus, periodic. They managed to extend this to the case of full plane using something called the Sarfati idea. It's a different way of writing UFRJ. Okay, so a summary of everything I've discussed. This is the end of the lectures. A summary of everything I've discussed is that, first of all, the point was that the Onsager scale is not the last word on inviscid dissipation, and that there is a two-dimensional mechanism to avoid anomalous dissipation. Another important point that I'm trying to make here is that vorticity transport, the relevant physical restriction on incompressible fluid flow behavior, and is completely ignored by all of the constructions obtained by convex integration. There's no vorticity transport. Case people 1 is still open. Since in view of the Untitled result, nothing actually, it's not likely to improve energy conservation because you have nowhere to come up with strong convergence for viscous vorticities, for the viscous velocities. There's no reason to believe that you're going to manage to find velocities you knew which converge strongly enough to because of the equivalence result. And it's kind of annoying because we know a lot about vorticity. We know that we have existence in L1, even more to the point, inbounded measures, vortices exist. And we do not know whether the TUR solutions conserve energy. We know that if you're in L1, the TUR type solution will conserve the L1 norm of vorticity, but we don't know what happens with energy. A less ambitious question, instead of energy conservation, is can you show if the vorticity is L1 that, and if you're a physically realizable solution, can it be attained by convex integration? Can it be a wild solution? This doesn't mean that I'm looking for a proof that it does or does not conserve energy, but can it be attainable through the standard convex integration type machinery construction? We have some reason to believe that this question is answerable in the negative. In other words, a convex integration can never lead to something which is physically realizable. But that's an awfully big statement. Vorticity in weak solutions obtained as limits of other approximations, not only vanishing viscosity, also conserve LP norms that are also renormalized, namely if you smooth that initial data, exactly solves the ordinary relations and pass to the limit, or if you solve the Vortex-Blob approximation. The Vortex-Blob method, that case that was done by Jenna Musiampa, John McNeiva, and Stefan Spiegel in 2019 or 2012. And finally, you can improve any kind of equivalence criterion with forcing a la Toller and Paul. Can we treat less regular forcing? We're not satisfied with the kind of forcing that we treated for the energy balance. And that's it.
Right. Questions, comments, audience? Yes,
So, is it possible to extend the framework to say you take this like 2.5, right? So you talked a little bit about axisymmetric, this kind of things, right? You said helical flows. It seems it's mostly just a structure that's needed in this similar embedding. So it seems like it should go, right?
For vorticity, probably, yes. Okay. For energy, well, again, you should have a result. There is a result for axisymmetric, but So what bothers him is it's not satisfactory in the sense that the exponents don't look right. On the other hand, these additional symmetries, especially axisymmetric, they're not really the homogeneous. There's like curved direction. That's something that may spoil some of these natural.
The axis symmetric with or without swirl?
Without.
No.
Without.
So
Yeah.
the answer to your question is no.
Swirl, yes.
Because she wants transport. The minute you have vorticity stretching, kaput, symmetry or not symmetry.
Yeah.
That's the short answer. That's why the axis symmetric is without swirl, namely transport.
And helical again, it would be the case of
Without
helical without helical swirl. Yes.
The whole thing is relying on this eternal
Yes.
machinery transport.
I have a question, but probably kind of it's situation for 3 actually elections.
I'm sorry.
What can you say about can anything of this be extended or tell us anything about flows with the walls?
Yeah.
At all? If but you have force.
Because
Okay,
basically because you're not going to have any vorticity estimates.
okay, but you have forcing. If that forcing would be in a some simple way, dependent on the velocity. So go back to word. Name minus constant positive, which depends on spatial point, times the velocity itself, minus k of x with such forces linearly, and k of x is an minus.
I would have checked, but I don't see a problem.
Because that is the standard way
I see.
we use in numerics to do walls.
I see.
Separated
Oh, that's
by
okay.
size. So you think
As long
then,
as you have an equation,
yeah, minus k,
yes.
this f minus k of x times s. But then, well, I got my k zero, flow is really large, positive way to the circle. And you think that then it will be also.
Problem.
That's it. I'm all into flows plus flows. Thank you.
Well, comment in this in the direction that we have a fairly recent paper with me, Helena Constantine, and what the Helena. Anyway, so we study. Okay, so we in a bounded domain. So now we have. Okay, and you know that there is this classical criterion by Kant that says that if you have convergence, if you have some control of energy dissipation near the wall, then you have convergence to weak solution or to strong solution. And it's only different. And we were always bothered by this because you don't expect that to happen. Take a sequence of solutions understood, send a viscosity to 0 in the bounded domain. You expect some mass happening in the boundary that will contaminate the flow inside, and you don't expect the limiting flow to be smooth. Okay? If we talk to Peter Constantine about it, Peter will say you don't expect the solution, the limit to be a weak solution coil at all. Okay? Whereas me and Helena will say, okay, maybe it is. You don't know. So we wrote this paper where we look right here instead of looking at the energy dissipation unit. Okay, we say we're gonna make an interior criteria. Okay, and we do that. We create two. So one is, and there is no Diracs happening at the limit. So you take the sequence of viscosity approximations, and suppose that you have some kind of control of the vorticity small balls inside, not near the boundary, just inside. Okay, so that you don't have Diracs. First, and the second hypothesis is that suppose that you have some kind of uniform L1 bound, again in the interior, not if you have these two things, then the limit is a weak solution. Okay,
It is a solution.
it is a weak
Yeah, this is an
solution.
extension of some criteria
What-
that Peter did with Vlad Vikul.
Yeah, that's our fourth pathway.
What kind of control on vorticity side? You said some type.
The control, what
There's
you need is,
two hypotheses. Okay, one, no Diracs arise in the limit. No Diracs in vorticity, so no point vortices arise in the limit.
Well, what about shear layers?
That would be okay, as long as the shear layer doesn't evolve into a point vortex.
Oh no, but this is a Dirac omega, but as a function of
no, this would be a Dirac on a curve,
yeah,
on the boundary. That's okay.
inside.
What
What
you-
will be on the bottom?
That's okay.
Yes.
That is okay.
That our criterion of acceptance. So
Yes.
This means non-null. If you had a null,
No, because everything what I'm talking about here is only cared about the interior. It's only interior aspects. We completely ignore what happens at the bound.
Well, okay,
But the other one is L1 bound, and this one is the one that we get very upset, and we have no idea if the approximating a Navier-Stokes problem has a global L1 bound over this. So you
With a boundary.
with a bound, yeah, with a boundary.
But okay, so let me be a little bit more precise. It's not a global L1 bound. What you need is, if you're in the interior, if you're at a distance from the boundary, okay, and you know that uniformly in viscosity, the vorticities are L1 at a distance from the boundary. Of course, the L1 bound could blow up as you go to the boundary. As you include more and more of the domain, that the L1 worm could blow up.
we are talking about time-dependent flow. So
Yes.
when you are saying
Yeah,
it's
yeah,
what in time?
Yes.
To the time dependent.
Is there a chalk here?
Because you see, it was many years ago, I forgot the law, but when I looked at that stuff, the main issue for me was that we do know what happens. There will be separation from the boundary into the flow. We will have rejecting themselves those shear layers.
That's
And
what
as vorticity tends, as viscosity tends to zero, they will become discontinuities and velocity. So deltas and wedges. And it looks like, and in that case, the point is the solution of Euler, which allows this, is not unique in the first place. You might have smooth solution of Euler, but at the same time, there are many other solutions, and the choice is done by viscosity. And that's with this cutoff where I stopped, because that was not there.
yes.
So you are saying that we now have more of this, and these are allowed.
Yes. That's
Well,
exactly what we were. That's the picture we had in mind, and that's exactly what we were.
this is the bound between this one and also a bound on the mass of the viscous vortices in small balls. It has to go to zero uniformly when the ball goes to zero. Inside.
L1 of K.
Yeah, so
What's
you
K?
take,
Case
So,
of compact
if my flow lives in a domain
Uh-huh.
omega, and I take any contact supported subdomain. If I know that it's uniformly L1 inside,
Which is
Uniform.
impossible to guarantee. This is
it's a
Uniformly in
viscosity,
and viscosity.
which is not correct, because then you exhaust the domain, you add more and more from the boundary layer. That
Well,
basically, that's what could be
no, but
growing and growing.
Idris,
Okay,
the
so-
constant can depend on the domain. This could blow up.
Yeah, so if a shear
Going up
layer
to the
will
domain, but
enter
not
K,
the
that's
viscosity,
not
that's the point. So it needs to be guaranteed.
If the shear layer enters K after some time, that is not satisfied.
It is satisfied. The shear layer is still bounded in L1. The shear layer is total. The point is total mass of vorticity to be bounded, and of course, a shear layer is a vortex shear.
Oh,
It's-
it is the total.
yes.
Okay, it's a norm of vorticity.
But this is for the
It's
viscosity,
L1.
but this is for the viscous flow. Therefore, for viscous flow, you don't have the shear layers that you expect for Euler.
But
The same way, if you take the vortic sheets as initial data and run Navier-Stokes, you don't have any long sheet. You will diffuse.
Oh, yes,
But-
yes, but
And
when
so-
it goes from the wall and when you require fixed time and then you want to have vorticity to 0 and you want to uniform bound on L1, but I need to figure out
So
L1.
at one point, we actually asked,
There's no reason
so there is
to imagine.
some experiments, just looking at what the vorticity coming out of the boundary is. We were talking to
Kai Schneider.
Kai Schneider about it. And we actually asked him, okay, so in your calculations, do you see an uniform L1 bound? Okay, he's actually simulating that. But the domain,
It's more than that. We saw his simulations, so we have some videos of his simulations, and you don't see either directs or L1 bound explosion.
Maybe you
But
can
we never-
send me a reference to this.
Yeah, it is published.
Of course,
Sure.
but just it's not my field.
communication,
What-
mathematical physics, when?
No,
Yes, a couple of years ago.
Okay, we should stop
Yeah.
this.
Yeah.
No,
And this is not the theme of
the other thing that
of
you
the
need
video.
is this stuff.
But it is very much connected to your question.
I understand. Yeah.
This. Okay, so you take the suit, you and time, and let's know.
In a compact set.
In a compact set,
In a
right?
compact
I mean, yeah. But I mean,
It's okay. It's in the same. Well, okay, well, there is this issue of the static vortex. There is this issue.
I'm sorry.
You see, this is okay for classical velocity discontinuity, right?
Yes,
Oh.
yes.
But with a static vortex, it's difficult to figure out what's going to be in that case. Let me explain what that is. If you have, for example, something like this, and this, oops, sorry,
Another one.
this is my wall, and I start flow like this. Then what happens is something like that. You know this. And while that is okay, but there is a solution to this.
That depends how bad the spiral is.
Yeah, if the current spiral is the right model, that's okay, because then the blow up is square root
Yeah.
of the vorticity singularity in the sheet.
So that's totally.
I simply don't remember what was there in because I never.
Yeah, the asymptotic model, traditionally, the asymptotic model of that spiral is a Kalman spiral, which is the vorticity blow up there is like a square root, 1 over square
One
root
over square root.
of. So the circulation, the point of the circulation in a small wall is not decaying linearly like in the near the sheet, but it's the case like square root of radius. It's still far from violating that condition.
Other questions or comments? By the younger, the youngest. Okay, well, thanks again, Helena, for the